Okay, let me draw first of all the real geometry. It's actually that one. Let me be more precise. Okay, I drew the profile of the Earth. The radius are 0, and I drew the profile of the electromagnetic ray that is bending with radius of curvature rho. And I'm considering here a coordinate x. So that this is the y-axis. So I call this distance. Can you see it, or it is too small? I call this distance epsilon b, and I call this distance epsilon g. So that the sum of the two is epsilon a. So okay. So in other words, epsilon c will be the height of the electromagnetic ray above the ground. Now what I want to have, as I said before, is a straight electromagnetic ray. So I take the electromagnetic ray and straighten it. I force it to be straight. So this is the distorted geometry. So this time my electromagnetic ray is propagating as a straight line along the x direction. But obviously, if I take this electromagnetic ray and I straighten it, what must not change is the height above the ground of this electromagnetic ray. That is, when I straighten up this electromagnetic ray, I'm also bending up the profile of the Earth. So my Earth profile will be distorted, but the constraint is that this distance does not change. Obviously, the radius of curvature of the Earth will not be the same. Will change, will be different from our view, because I am distorted with geometry. But the good thing is that the electromagnetic ray now is propagating along a straight line, and it is easier to deal with. Now, our target is calculate the new radius of the Earth. Because once you have the radius of the Earth and you have the profile, for example, on a digital map on a digital terrain map, what you do is you take this digital map, like one from Google Earth, but there are other sources, and you just curve it with the equivalent radius. And then you use it with straight electromagnetic rays. Okay, let's calculate the equivalent Earth radius. How do we do it? Well, we force those two quantities to be the same. In particular, as I said, from this equation, epsilon c is equal to epsilon A minus epsilon B. Okay, those are circles. But if the distance, this coordinate, is much smaller than the equivalent radius or the curvature or F0, and this is true if we are talking about radio links. Because if we're talking about radio links, we are talking, if this is the transmitter, we're talking of distances from the transmitter of 10 kilometers, 100 kilometers, much smaller than 6,300 or 27,000. So this condition is always verified. If this is the case, as you possibly remember, those circles, because those are circles, arcs of circles, can be approximated with parabolas, parabolic profiles, parabolas. And so you can write as a first approximation the following expression for those quantities. If this is a parabolic profile, then epsilon c is divided by the radius of curvature. This is the definition of radius of curvature of parabolic profile. Epsilon A, that is this profile, is going to be and eventually epsilon B, this coordinate, is going to be this. Remember, this is a parabolic approximation. So we make up, this makes our life much easier than using circles, because circles are pretty nasty to deal with. So, we take these things and we put in that equation. What we get? Something that really blah 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 is square divided. And all those factors cancel out. So you end up with this equation that is very simple. And everything is known but the equivalent at radius. And if you remember that minus 1 divided by rho, that is this term here, is equal to dn divided by dh. We found that before. You take that, you replace it there, you find out this expression this is called the K factor. So we say, okay, our distorted Earth planet is K times the Earth, the radius of the Earth. And now we're going to see what that K, what's the value of that K for the standard atmosphere. In standard, that is median. If you put in 27,000 kilometers here, you put the value in this equation, you find that K is 4/3, more than 1. That is, the equivalent radius is 8,500 kilometers. When you do a radio planning and you want to use the average atmosphere, for radio planners, the curvature, the radius of the Earth is 8,500 kilometers. It's not 6,360. All the calculations for standard atmosphere are done assuming that our planet has a bigger radius. A bigger radius means that our planet is more flat or more curved. It's flatter. So, if you do a radio, if you put an antenna over a hill, over a mountain, you expect the coverage of the radio system to be bigger or smaller than the geometrical coverage. Bigger. And in fact, the radio horizon goes over the geometrical horizon. And it will change with time according to the status of the Earth. And we shall, in the minutes that we are left, I want to discuss the situation, the statistics, pretty simple, of the gradients of the atmosphere. There are questions so far? Yes, please.
I have one question.
Yes.
This or that D and DH is delta N and delta H.
Yes, this is N, sorry, and this is H.
But delta or that D stands for another.
Yes, it is actually, delta is, this is the derivative. And delta is an incremental difference, but when the difference tends to 0, they are the same. So they are, it's the gradient, it's the derivative, also in the other case. Other questions?
I have a question. The radius of plus or at the highest elevation for this is
8,500 kilometers is the radius.
you have the mountain elevation or no?
Sorry. Say it again.
You are plus the radius of here that is 6,000.
Yes, it means that if you have a ground profile, a real profile, geometrical profile of the Earth that is like this, and this is the average height, the distorted geometry will be, let me draw it in more dramatic way. and this is the sea level. You just have to redraw the sea level line with that curvature, with 8,000 instead of 6,300. So it will be flatter. And on top of this, you have your rocket. So you take the line, the hypothetical line of the sea level, and that line has a natural curvature of 6,370 kilometers. And on top of that you have mountains, buildings, whatever. So you straighten up that line, and all the buildings, mountains, etc., they follow that line. That's the way you do it when you do the calculations. Okay, now if you just an anticipation of what we will see later on. If you make a statistics, you make an observation over time of your gradient. Suppose you measure it. And you measure it over time, and you observe this over, say, days or months, years, and then you plot the statistics. You find something interesting. Since temperature, pressure, humidity is varying in time continuously, depending on the season, on the day, the night, etc. If you draw the probability density function, you find that on average, your atmosphere shows a gradient of minus 37 kilometers to the minus 1. But the variability around that average value is huge. Find a very large distribution around the average value. Let me just put a couple of important values that we'll discuss next time, that are 0 gradient and minus 157. Now the problem that you have to face is, given this variability, statistical variability, which value of the refractive index gradient you have to use. Because if you take the standard atmosphere, that's only representative of an instant in time. This anticipates something that we will see later on, that is, it is not possible, and I want to underline this, it is not possible to design a system where the transmitter and receiver see each other 100% of the time, unless they are few meters apart. It is not possible. Because statistically the refractive index will vary, your curvature will vary, and at a certain time your receiver will disappear below the horizon. You have to decide, and it's up to you, what is the percentage of time that you can tolerate for your receiver to disappear. How we do that will be next time topic. questions? Thank you. See you tomorrow. Hasta mañana.
Lo que decía era si era mayor o menor en la plancha de bobina. Sí, ya. Lo que es mayor. Porque, por ejemplo, tú ves la regla de Gris, te quita esa corrección. Baja aquí y acá. ¿Y qué es lo que pasa? Era mayor cobertura o menor cobertura. Era mayor cobertura porque la antena no se ve los rayos hacia abajo, sino también se refleja y puede caer más allá de la antena.